Okay, let us start the lecture. And at first, we will consider generalization of Donsko's theorem, and then we will consider stochastic processes with reflection. So the plan is the following. Assume that let xk be a Markov chain with values in finite state space in a finite set E, and we assume that all states communicate and let us consider the following process. Sum k from 1 to n f of xk, where f is a function from from E to R. We have already known the law of large number for yn. We know that limit Sn goes to infinity, yn over n is expectation of f of x0 if initial distribution is stationary. And we also discussed that this immediately implies the following, that for every t greater than 0, we have, okay, let me denote this by A, that scaling limit of yn minus at is zero almost surely. So in some sense, these sums behaves approximately like sum of independent identically distributed random variables. And now the second step is, let's consider Donsko's scaling. Let us divide by square root of n, but we subtract at in the numerator. So the question is, what is the limit of ynt minus ant over square root of n and we will consider convergence in distribution. Okay, and let me recall that I will that in Donsko's theorem and in other results, I define y for non-integer values by linear approximation, and this convergence, if I prove it, will be considered as a convergence in the space of continuous functions with topology of locally uniform convergence. Okay, so let me represent this as the following. So consider the process yn, which is some k from 1 to n f of x k minus a. So then y of nt minus a and t over square root of n is just Donsker scaling of the sequence y tilde. I would like to stress that these random variables are not identically distributed in general, because xk is a Markov chain, and they are not mean zero. Well, what do we know? We know Donsker scaling and some results of this type, and I wish to find independent, identically distributed random variables in this scenario. So let these be time, so n, this be a state space. We fixed certain value I, for example, and consider Markov chain x of n. So this is Markov chain x of n. Now we find moments when the Markov chain hits this level. This moment, this moment, this, and this. And it follows from the strong Markov property that behavior on this interval, this interval, this interval, this interval are the same and independent. And let me denote this instant by okay. So let this distance be eta 0, this distance be eta 1, this distance be eta 2, this eta 3, and so on and so forth. It follows from the strong Markov property that eta 1, eta 2, eta 3, eta 4 are independent, identically distributed random variables. So eta k greater than or equal than 1 are IID. Well, eta 0 is exceptional because we don't start from this fixed point I. Moreover, we know, and we know even the formula, how to calculate the expectation of eta k. And we know that this expectation is finite. Yeah, we assume that the state space is finite and all states are, so all states communicate. So we have this. Now, let's consider this excursion or this interval between two so-called renewing or regenerative moments, and denote by psi k sum I from, okay, so let this number be tau 1, this tau 2, this tau, okay, this point tau 1, this point tau 2, this point tau 3, and psi k with the sum I from tau k to tau k plus 1 minus 1 f of xi minus a. These psi k also are independent and identically distributed random variables. Identically distributed random variables. By the way, please remember the law of large numbers and the way of proof. And they're not only independent, identically distributed by expectation of psi k is 0. Well, the sum here is psi 0, so it may be different. It may have different distribution. The next exercise is this. Okay, this is exercise. Prove that expectation of tau k of the so that the second moment of tau k is finite. Then, if you prove this, then the second moment of psi k is also finite. Indeed, there are ak summands here. So psi k squared is less than or equal to eta k times maximum of f of absolute value, okay, plus a, and times eta k, okay, and this is just a constant, and square expectation of eta k is less than infinity, so expectation of psi k squared is finite. Well, and we know that the sum of xi's, the Donsker scaling of random walk with increments xi that are IID converges in distribution to sigma times Brownian motion where sigma is variance of psi k. And now you see these intervals are also IID. And this scenario we have considered in the previous lecture. So consider the process as psi of inverse of eta of nt over square root of n. So what is this? We wait the time eta 0, and then we jump to xi 0. Then we wait eta 1, and the next increment is psi 1. Then eta 2 and increment psi 2, and so on and so forth. And we consider linear, oops, no, excuse me. Okay. We consider the linear approximation and so on and so forth. We know that this process converges in distribution to sigma times Brownian motion divided by square root of eta, so divided by square root of a. And now a question. Is this stochastic process y tilde of nt over square root of n or not? So what do you think? Other ideas? Well, the answer is no. The answer is no. This process coincide, so this process coincide with y tilde only at this instance of time. But y tilde may be different here. So, but let's discuss what is the difference between y tilde and this. So let's consider maximum, say t in, okay, consider interval 0, 1. Y tilde of nt over square root of n minus s psi of s eta inverse of nt divided by square root of n. Both processes are linear between natural numbers, and if t in 0t then nt is in 0n, so this maximum is attained when nt is natural number and is equal to difference y tilde of k minus s psi of s eta inverse of k divided by square root of n. Well, and I wish to say that, okay, so the maximum here, the maximum is 0, there, and so on and so forth. So this maximum, so let me write and then we will discuss, is less than maximum j between 0 and n maximum I between eta k and eta k plus 1 y tilde of y minus s psi as eta inverse of I divided by square root of n. So I consider the maximum, the first interval, on the second interval, third, and so on, and so on, and so on, and so on. And I know that eta k is greater than k, so actually here, this maximum is maximum over interval from 0 to eta 1, eta 0 plus eta 1 plus eta n, which is greater than n. Yes?
Is over J or over K?
Over k, over k. Let me write
Mhm.
j here. Yes, another index. So this is greater. And why do this expression better than this one? Because if j is greater than 1, then these random variables are independent, identically distributed for j greater than 1. And it is not so, it's much easier to study the distribution of maximum of ID random variables. Okay, the first interval divided by square root of n, so maximum of the over this interval over square root of n converges to 0 almost surely. Okay, for all omega. And for other, the distribution of maximum is the distribution of this. You start this interval. So this interval, Markov chain start at I and end at I, and you consider supremum of the difference. So let me denote, okay, let's consider. So let's discuss this at j at j plus 1 y tilde of yes, y tilde of k minus what? Minus this process. Minus s psi s eta inverse. Okay, I here over, well, consider this. The distribution of this behaves like the following. So we start Markov chain. Assume that we start from I, that point. We walk and we end at I again. And we have to consider this difference over this period. And okay, the exercise is to prove that absolute value here. Excuse me. The first exercise is to prove that the second moment of this exists. Well, you know actually that At each step, you add a random variable which is just bounded. I mean this one. And you know everything for this. So this random variable has a finite second moment. And another exercise is the following. Assume that expectation of certain random variable, so second moment is finite, where zeta j are IID. Prove that maximum of psi j over square root of n converges in probability to 0 as n goes to infinity. If you have this, then you know that the maximum between our stochastic process and the stochastic process goes to 0. So maximum over finite interval goes to 0 in probability. And this is almost all. Well, consider not C0 infinity, but C0t. So this metric space, we know that there is one sequence of random elements, this one, the scaling of this one, that converges to a Brownian motion, and another, and the difference goes to 0 in probability. We discussed Slutsky lemma that if one sequence has a limit and the distance between the second and the first is small, then the second also converges to the same limit. And that's all. So corollary, the scaling of the sequence y tilde also converges to a Brownian motion times certain constant. So to prove this theorem, so what do we really need? The first one, result about this sequence scaling of xi of this inverse. Then we need to prove that expectation of these etas are finite and that they do really have the second moment. We need the following estimate and this fact from probability. Well, all steps are quite elementary, but when you combine them, you obtain a non-trivial result on scalings of additive functionals of Markov chains. We also assumed that the state space is finite. This simplifies a lot many things. For example, if the state space is finite, then immediately you have the finite moment here and second finite moment and so on and so forth. If xk is a Markov chain on infinite state space, then you need to demand some recurrency and some other nice properties. Yeah, we for general Markov chain we don't know is what about the law of large numbers, or is it true that expectation of xi squared is finite or not? Then we have to impose additional conditions. Okay, questions? If no, let us continue, and we have finished the section scaling limits of random walks, Donsker theorem, and its generalization. And now we begin a new topic that is called stochastic processes or stochastic sequences with reflection. So this is the first example of perturbed random walk. So the general problem is the following. Assume that we have a random walk on the upper half line. Well, assume for a while that the expectation of a jump is 0 and the second moment is finite. So Donsker scaling should be close to a Brownian motion if the random walk is above 0, and assume that 0 level is unpermeable. That if the random walk is such that its increment is such that you wish to jump to the negative half line, then you reflect somehow. Okay, so this is reflection. So it wishes to come here, but you reflect. And if you are at the positive side, then you again add independent, identically distributed random variable. Then you wish to cross 0, you reflect somehow, and again you add ID random variables. There are many natural types of reflection. The first one is this. So if you wish to jump here, then just flip this point and place your random walk here. But there are other and also natural. Let's start with the first example that is called Lindley's model. Well, the setup is this. Let xi k be ID, random variables, and let x0 be non-negative random variable such that x of 0 and the sequence are independent. And I wish to construct sequence xn in the following form. So it will be non-negative, and interpretation will be like amount of goods in a storage at instant n. Amount of goods in storage, or maybe xn is the level of water in a lake. In a lake, or xn at the moment n, or the number of requests in a queue, number of requests in a queue at instant n. And let me interpret psi n as a number of requests that arrive minus number of requests that were processing at the moment t. So psi n is arrival of water and evaporating of water, or you sell some goods, but you refill your storage also. And when you sell, so this is random variable. So arrival minus departure. So Lindley proposed the following recurrence for xn. So xn plus 1 is equal to xn plus psi n plus 1 if this number is positive. So assume that you have certain amount of goods. At the beginning of day, you refill your storage, and then you sell goods. And assume that people want to buy more than you have. So assume that this instant n plus 1, and assume that people want to buy more than you want. Then what is the result? You sell all the goods and you have 0 in a storage. So if xn plus xn plus 1 is positive, then amount of good is this. Otherwise, if it is negative, then 0. And the random walk jumps to 0 and then start from the beginning. Then start from the beginning. If this amount is positive, then you jump above and you add size and add size, but sometimes you wish to cross 0, then you just jump to 0. Maybe at the next step you also jump to 0, and if increments are positive, then you just add independent and identically distributed random variables xi. So in some sense, this is a reflection. You see, you add IIDs here. If you wish to cross the unpermeable level, you just stuck at this unpermeable level and start from the very beginning. You add IIDs and so on and so forth. Well, so formally xn plus 1 is equal to xn plus psi n plus 1. Sometimes people write like with plus. So this number, if this number is positive, and 0 if this number is negative. Or sometimes people write like xn plus psi n plus 1 maximum with 0. So if it is positive, then this number. If it is negative, then 0. So this sequence is called a Lindley's recursion. And one of our aims is to find scaling limits of linear recursion. For example, if psi k are IID, zero mean, finite variance. So the guess is the following. It should be the limit process, if it exists, should behave like a Brownian motion above zero, and it cannot cross zero. So it should reflects somehow. And we will see that this is reflect the result is a reflected Brownian motion, just absolute value of Brownian motion, but we have to prove this result rigorously. So this was a motivation for reflection, and we considered two examples of reflection. The first one was like this. The second natural reflection was Lindley's recursion. And the subsection of today's lectures is called Skorokhod reflection. Skorokhod map. And Skorochod's map. Well, idea of Skorokhod was to construct reflected diffusions and to find a natural possibility for reflection. And he started with a deterministic problem. So he considered non-random continuous function. So let w of t greater than 0 be a continuous function. That started from non-negative point. And well, my interpretation of Skorochod's problem is this. So the function w of t is a program of a robot that walks up and down, and assume that there is unpermeable wall at 0. So until hitting the wall, the robot walks according to his problem. But when it hits wall, and if the program says go down, like here, the robot cannot pass through the wall. So the robot, it stays near the wall. But if the program say, okay, goes up, so the robot stays here. And then program say, oh, go up. And then robot goes up. Then the program says go down, robot goes down, and then stack the wall again. The program say go down, robot can't, so it stays near the wall, and then again it goes up, down, stay near the wall, then the program say go here, and so on and so forth. So the aim of Skorokhod was find a position of a robot at instant t. So he proposed the following problem. Find so Skorochod's problem is, actually this is the name, Skorokhod problem. Find two functions x of t and L of t such that, well, X of t will be position of a robot. Such that, okay, the position of a robot is non-negative. The second, what is the position of a robot? Position of a robot is equal to this program plus effect of the wall. What do I mean? So when the program says go down, you may think that the wall pushes robot up in such a manner that robot stays near the wall. And well, when robot goes up here, there is no effect of the wall at all. But okay, X of t is the sum W of t plus L of t for all positive t. And the third is this function L is non-decreasing, so the wall pushes only up. L of 0 is 0. This is just normalization, and that at the instant 0, there is no push. And that L may increase only at the instance when the robot is at the wall, near the wall. So this means the following, that integral from 0 to infinity indicator x of s strictly greater than 0 dls is 0. So the wall does not push if the robot, if xt is here. So L do not increase if x is here. So L may increase only when x of s is 0. So sometimes this condition is equivalent to this. L of t is equal to integral from 0 to t dls. So this is always true, but the integral with indicator that x of s is 0. This means that L may increase only at the moment when robot visits 0. Well, and Skorokhod also considered continuous functions, so he demanded that x and L are continuous functions. So x and L continuous. So this is a formulation. It is not clear that solution exists. For this particular picture, x of t is the following green function, as we discussed. So it goes as red function before the first heating, then stays at 0, and okay, then it's continuous. Continue like this, and the function L is. So let me make a picture. So the wall does not push robot at all before the first heating. Then robot wished to go down, so the wall compensate this level. So this is just symmetric part. Then robot goes up, and L is not increasing until the moment when you hit 0 again. Then the program says goes down. So the wall should compensate like this. And then robot is above 0, so there is no compensation. Then robot wishes to go down, so the wall should compensate up. And then Okay, robot is at the positive side. Then, okay, then this picture. So for this particular smooth function, solution of the Skorokhod problem is a pair. This green function is x, and this brown function is L. And the first result is the following important theorem that for any W continuous functions such that W of 0 is non-negative, there is a unique solution X and L. So to the Skorokhod problem, to Skorochod's problem. And this solution, moreover, there is a formula. Moreover, L of t is equal to minus minimum of W of S minimum 0 as in 0t. Well, and x of t is a sum W plus L. So x of t is W of t minus minimum of W of S minimum 0 as in 0t. Okay, so this is result. Alternative formulas that you may find in the literature for these are, for example, minus minimum of W of S minimum 0. So you may consider this. Or minus minimum is equal to maximum of minus W. Maximum of minus W of S and minimum with 0. So sometimes people say for this running minimum. Well, let's see what is the running minimum of W and minimum of 0 on the previous picture. Okay, so one moment. Okay, let me just rewrite the formula. So I wish to calculate minimum of minus minimum of W of S and minimum with 0. If W is on the positive side, then minimum is non-negative. So minimum of these two is 0. Then minimum of W is this, and it's less than 0. So the formula is minus of this point. Then minimum for every t for then minimum on this interval, for every t from this point to this point, minimum is attained here. So the running minimum on interval from this point to this point, or from this point to this point, is equal to this value. So the running minimum is this. So without this meaning this and this. Well, consider a point here. So what is the minimum of W of S? It's attained here. So the running minimum is equal to this part. And then if t is at this interval, the running minimum is equal to this value. So this is a picture. This is a picture. Well, and after this instant, minimum of these two is equal to this. And if you look here, then the trajectory of L is minus this running minimum of W. So this was explanation. And I will not prove that this formula is really a solution. So prove that L and X is a solution. To the Skorokhod problem. So actually it is not a problem. You just need to verify three conditions. X is non-negative. Well, more or less it's obvious. That L is non-decreasing. Well, it's also obvious. That X is equal to double. Yes, X is equal W plus L. Yes, we have this. And all of these functions are continuous. Yes, not a problem. The only thing, maybe non-trivial, is to see that L does not increase if X is positive. Well, if you look at the picture, this more or less obvious, but well, maybe some additional reasoning are needed, but not so much. I'm going to prove uniqueness. Uniqueness, well, we have one solution, and assume that there are two solutions of a Skorokhod problem. So let x1 L1 and x2 L2 are solutions to Skorochod's problem. Consider the difference x1 of t minus x2 of t. I'm going to prove that this difference is zero. So what is x1? x1 is equal to w plus L1 of t. X2 is w of t minus plus L2 of t. W is cancelled out, so the difference x1 minus x2 is equal to L1 minus L2. And this is non-decreasing function. This is non-decreasing function. The difference is a function of a bounded variation. Okay, continuous function of bounded variation. function of bounded. So the left-hand side is also continuous function of bounded variation. Well, then x1 of t minus x2 of t squared is equal to integral from 0 to t to x1 of s minus x2 of s d x1 of s minus x2 of s. Well, this formula is well known from mathematical analysis if x1 and x2 are continuously differentiable, but for continuous functions of bounded variation, this formula is also true. And now let me replace x1 minus x2 with L1 minus L2. The L1 of S minus L2 of S, and I represent the corresponding integral as difference of two integrals, minus integral from 0 to t to x1 of S minus x2 of S dl2 of S. And now, interesting observation. So L1 increases only, so it may increase only when x1 is 0. So the first integral is equal to integral of these functions times integral x1 of s is 0 dl1 of s. So let me recall the Skorokhod problem. So L of t is equal to integral from 0 to t, indicator of x of s is 0 dls. So dlt is equal to indicator x of t 0 dlt minus make the same procedure here, but let me write indicator x2 of s is 0 here, dl2 of t. Well, indicator equals 0 if x1 is not 0, and equals 1 if x1 is 0. So this integral is equal to integral from 0 to t, 2 times minus x2 of s, indicator x1 of s is 0, dl1 of s. So if x1 is positive, then indicator is 0. If x1 is 0, okay, I don't write it here. Minus integral from 0 to t to x1 of z, and again, with indicator x2 of s is 0 dl2 of t. Now, x2 is non-negative, so with minus, it's non-positive. X1 is non-negative. This is greater than 0, and don't forget about this minus. L is increasing function, so this integral is non-positive. This integral is non-negative, but we have minus here. So this difference is non-negative. What does it mean? This means that x1 of t minus x2 of t squared is a non-positive number. How it is possible? Oh, I'm sorry, excuse me. I forget here to write x1 of t minus 0 minus x2 of 0 squared. Oh. Uh, but if x1 and x2 are solutions, we know that L1 of 0 is 0, L2 of 0 is 0, so x1 of 0 is equal to W of 0, and x2 of 0 is equal to W of 0. So this term is equal to 0. So I didn't make a mistake. So this is 0, this is non-positive, this is possible if and only if x1 is equal to x2 for all t. And theorem is proved. Okay, questions? Well, if no, let us continue. And let me introduce the notation. So the function that maps w to x, so the formula will be denoted by gamma. So gamma of w is a function of t is equal to w of t minus minimum of w of s minimum 0. This function is called Skorokhod map. Is called the Skorokhod map. So it maps from the space of continuous function that start from non-negative number to the space of continuous functions. And we know, moreover, that x is non-negative. So we may consider gamma as a map from C0 infinity to C0 infinity, or sometimes from C0t to C0t. Well, this is Banach space, this is just metric space, and the first property of the Skorokhod map is its continuity. So for any t greater than 0, for any w1 and w2 continuous functions, maximum t in 0 t gamma of w1 of t minus gamma of w2 of t is less than or equal to 2 maximum t over 0t w1 of t minus w2 of t. So in this space, gamma is Lipschitz function with the parameter 2. Well, and if you have this, then you may see that gamma is also continuous as a map from this space to this space. Okay, the proof. So maximum t over 0 t of this is equal to w1 of t minus running minimum minus minus w2 of t, again minus running minimum of w2 and absolute value of a sum is less than or equal to sum of absolute values. So this expression is less than or equal to maximum of absolute value w1 minus w2 plus this minus this. So plus minimum w1 of s minimum 0 minus minimum s in 0t 2 of s minimum 0. And we know that maximum of a sum over certain set of indices is less than maximum of this plus maximum of this. So less than or equal to maximum of w1 of t minus w2 of t plus maximum of this. And the next step, it's known from mathematical analysis that this difference is less than or equal to maximum of differences, absolute value of w1 of s minimum 0 minus w2 of s minimum 0. Well, it actually, it's not so complicated to prove. Well, you have two functions, two continuous functions. Assume that minimum of one function is attained at certain point and minimum of another is here. So this means that this minimum is, okay, difference of minimum, so this distance is less than or equal to maximum distance between between two functions. Well, it's more or less obvious. Indeed, this difference is less than or equal to this difference. And so this is less than this. And let me write one more maximum. So I take maximum over all t, and then I consider s from 0 to t small. So this double maximum is equal to 1 maximum, where s between 0 and t. So I consider maximum over all s, w1 of s minimum 0 minus w2 s minimum 0. Well, and this difference is less than or equal to w1 minus w2, just absolute value. So less than or equal to maximum of w1 of s minus w2 of s in 0t. Okay. So we started from difference of two processes, and the first maximum over 0 t capital and the second maximum, okay, t capital, and the same maximum. The theorem is proved, so the Skorokhod map is indeed continuous in the space of continuous functions. Are there any questions? If not, then example. So let psi k be ID. Expectation of psi is 0 and variance of psi is sigma squared. Let us consider Lindley recursion. Xn plus 1 is equal to xn plus xn plus 1 maximum with 0. And it can be seen, so if we consider as psi of n, which is equal to x0 plus xi1 plus xn, then x of n is equal to Skorokhod map of s psi of n, where n is integer number. Indeed, and let me recall that we extend psi by linearity for non-integer n. So what do we do when we consider Lindley model? So assume, so if xn plus xn plus 1 is positive, then increment is xn plus 1. So increment of x and of Sn is the same. So this is analog of W. But when x wishes to go below 0, then x stays at 0. Then x stays at 0. If psi is positive and you jump up, then increment again of W and of x are the same. And in some sense, x can be represented as W plus certain compensation. And what do we know? We know that S psi n t over square root of n, that this process converges in distribution to a Brownian motion. Then we know that gamma is continuous map. So by continuous map theorem, gamma of s psi n t over square root of n converges to gamma of sigma of b. Okay, maybe I have to write here dot. And without this parenthesis. Okay, so this is a function of t, and this is again a function of t. Well, gamma actually is not linear, but nevertheless, it can be seen that this is nothing else but gamma of s psi of nt over square root of n, or x of nt divided by square root of n, and this is sigma gamma of b. So corollary is this. So scaling limits of Lindley's model is the following process. Sigma w of t minus minimum s over 0 of t. I have to write here w of s minimum 0, but, oh, excuse me, not wb, Brownian motion. So Brownian motion, and we know that Brownian motion starts from 0, so I may not write here minimum 0. So the limit of Lindley's reflection is this process. Sometimes the process, this process, is called reflected Brownian motion. Bt minus minimum b of s is called the reflected Brownian motion. The reflected Brownian motion, or, okay, let me write like Skorokhod, with Skorokhod reflection. You may ask me the following very natural question. Sometimes the process absolute value of b of t is also called the reflected Brownian motion. What about this process and this process? So the first question, are they the same? Well, the answer is no. They're different. However, it can be proved, and we will prove it next week, that the distribution of absolute value of Brownian motion coincides with distribution of Skorochod's reflection of a Brownian motion. So in some sense, this reflection is quite natural. And we see this reflection is a continuous map and it appears naturally from certain type of reflection like Linley model. Okay, and probably that's all for today. Thank you for your attention.